Okay, this is Calc D Note 7, page 6. We're going to be doing a couple of double integrals over non-rectangular regions. So let's take a look at the first one. So let R be the region bounded by x equals 1, x equals 3, y equals 2 minus x squared, y equals 6 minus x squared. And then we want to evaluate the double integral over the region of x cubed. So x cubed is the ceiling, and then our region in the xy plane we have to describe, write our bounds, and then do the integral. So let's start with a graph. So I just used GeoGebra to get this graph because I didn't want to make you watch me do this, and also sometimes I fumble with these graphs. So we have this, and you can see 6 minus x squared is definitely on top, 2 minus x squared is on the bottom, and then obviously we're going from 1 to 3. So let's write down our bounds. So we have a top, we have a bottom, and we're good to go. So here we go, from 1 to 3, and then from bottom to top. And now the integrand is just x cubed. There's nothing, that kind of like doesn't play a role until you're done setting it up, and then, you know, it'll be a part of your integrals, and we're going dy dx. All right, so this one's pretty straightforward. We keep the outer integral, and we're going to integrate dy, but we're just integrating 1 dy, so x cubed is a constant, and then we just get y, because the integral of 1 dy gives you y, and y is going to go from 2 minus x squared to 6 minus x squared, and then we still have dx, because we're going to have to finish the integral. So now we're going to fundamental theorem where we're subbing in for y. Remember, we go upper bound and then lower bound. So the upper bound is 6 minus x squared minus the quantity, the lower bound. You want to put that lower bound in parentheses so you don't screw up distributing the negative sign. So all the stuff in parentheses actually just simplifies down to 4. So we'll have 1 to 3, x cubed is still there, and then this is just 4 and dx. And so the integral of 4x cubed dx is just x to the 4th. So now we're going to have x to the 4th from 1 to 3. And we plug in, and we get 81 minus 1, which is 80. I decided to check this one on the calculator just to show you that you can do that. So you just do, you know, the integral of the integral, plug in the bounds, plug in the integrand, get your answer. All right, let's take a look at the next one. So R is going to be the region in quadrant 1 bounded by x squared plus y squared equals 4, such that y is greater than or equal to 1. So there's kind of a lot going on there. We're in the first quadrant, we're bounded by this circle that has a radius of 2, and y has to be greater than or equal to 1, so a lot going on. We want to evaluate the double integral over this region of our surface, like the thing that's giving us the ceiling, x over y dA, which means we get to pick the order. So I'm going to start with the picture again. I think, or actually, I guess I'm going to choose to solve this for y first, which is really the wrong order to do that in. But I decided to do it, right? It's the top half of the circle because, let's look at it. This is our region. We have to be in the first quadrant. We have to be in the circle that has a radius of 2. And we need y to be bigger than 1. So it's got to be that shaded region there. So I decided to solve for y. This looks to me really like a polar region. So we'll deal with that later on in the course. We're not up to that yet, but this feels like a region that you could describe really well with polar coordinates, and it would probably make the problem a little easier. But for now, I need to know the bounds that I'm going to use. So I'm just going to figure out when the circle equals 1. So I get that x is root 3, really plus or minus, but we're in the first quadrant. So we have this, and I think we're ready to kind of set up our bounds. So it does look like a polar region, but we're not doing that yet. But that would maybe make this easier. All right, so the x bounds are going to go from left to right, so from 0 to root 3. And then the y bounds want to go from bottom to top, so from 1 up to the circle. So 0 to root 3, and then bottom is 1, and top is that. Our integrand is this, and we're doing dy and then dx. All right, so I'm starting to think this might have been a bad choice. Because I'm going to introduce a natural log like immediately, because the integral of 1 over y dy is natural log of the absolute value of y. But we're going for it. All right, so here goes. That's going to become the natural log of the absolute value of y. Now, thinking this is a bad choice, what I could have done at this point is kind of like abandon ship and just do it dx dy instead of dy dx. Might have been easier. I think at the end I'm going to do that just to see if it was. I got to sub in So still have this. Natural log, absolute value of this square root thing, but the square root is always positive, so we don't really need it. And then when I plug in 1 for y, I get the natural log of 1, but the natural log of 1 is going to be 0, so that'll zero out. Okay, so that's going to zero out. I said I thought this might be a bad idea. The natural log of the square root of 4 minus x squared, that's 4 minus x squared to the 1/2. I'm going to bring the 1/2 out as a coefficient. So I'm doing the exponent becomes a coefficient. So it's going to become 0 root 3. I'm going to have 1/2 times x. So that 1/2 is the exponent of 4 minus x squared inside the natural log. I brought it out because I think now I can integrate this. The issue is I need to do like a u substitution where u is 4 minus x squared, and then negative 1/2 du is dx, and I'll end up just integrating natural log. But I need to know how to integrate natural log. So I have that memorized because it comes up a lot. If you don't have it memorized, you have to do integration by parts, where you do the thing where u is natural log and dv is dx, and then you just integrate from there. But I have it memorized. The integral of natural log of u du is u, natural log of u, minus u, and then plus c, but we're doing a definite integral. So, okay, that's a lot of talking, but what I'm going to do is I'm going to let u equal 4 minus x squared. So then du is negative 2x dx. So I need a negative 1/2 in here because there should have been a negative 2x and I only have x. So I need a negative 1/2. So that's going to give me 1/2. Then I get a negative 1/2 from my u substitution. Now I'm just integrating the natural log of u, where u is 4 minus x squared. So that's going to be u natural log of u minus u. But u is 4 minus x squared. So it's quantity 4 minus x squared, natural log of 4 minus x squared, minus the quantity 4 minus x squared. I'm filled with regrets for having done it this way, but it is the way that I initially did it. I kind of fall for that. I say that, like, people always do this. I'm one of those people. I always try to do dy and then dx. Not always the best choice. Negative 1/4, and now we're plugging in. So 4 minus 3 is 1, and so that comes up a bunch. And then when you plug in 0, you get 4 natural log of 4 minus 4. So that's just fundamental theorem. And we can clean this up a little bit. The natural log of 1 is 0, so that's just like gone. So I combined everything that I could in there, and I'm getting the natural log of 4 minus 3/4. So that's what we get. I probably should have shown more work along the way, but it was a lot of work to begin with. Was this a bad idea? I think it was definitely a bad idea. I'm going to go back and do the problem the other way just to show you it's a better choice. So same problem. This is what it looks like again. Instead of solving for y, I'm going to solve for x. I'm going to say that x is the square root of 4 minus y squared. This has a lot to like, right? Because first thing I'm going to do here is integrate with respect to x, which will just give me 1/2 x squared. It's going to be so nice. All right, let's set it up. So x has to go from left to right. So that's going to be from 0 to square root of 4 minus y squared. Y has to go from bottom to top. So that's going to be from 1 to 2. So we're going to start with that because you start with the constant functions. And then we go here, and then our integrand, and then we are doing dx dy. And you can see already this feels like it's going to be easier. So 1 to 2. The integral of x is 1/2 x squared. So I'm pulling out 1 over y. It's a weird way to write it, but it's kind of in the way. So 1/2 y squared, x is going from 0 to this radical. But when you square the radical goes away. So that's also really nice. So I'm going to still have 1 over y, but now I just have 1/2 quantity. So I'll get 4 minus y squared. And when I plug in 0 for x, I just get 0. So that part's done. All right, so what am I going to do now? I'm going to take out the 1/2, and then I'm going to break this into like 2 integrals, basically. So I'm going to make it 4 over y, and then y squared over y is just y. Integrate this. A natural log is bound to show up because there's a natural log in the answer, but like look how much easier it was to get to this. So 4 over 2 is 2, and then you get natural log absolute value of y. Then you have to distribute the 1/2. So the integral of y is 1/2 y squared, but there's that 1/2 coefficient, so that's where 1/4 is coming from. You get this. Now we're just going to sub in 2 natural log of 2 minus 1. That's when we plug in 2. Minus quantity. when you plug in 1, natural log of 1 is 0. That happens a lot. You really got to be on top of that property. We have this, and if we simplify this, we get the natural log of 4 minus 3/4. So I didn't say that it was going to be easy, but I do think that this was a much more straightforward approach, and you should always be thinking about that. I should have been thinking about that. Although if I had done this first, I probably would have been like, hey, let's do it the other way. So I was going to do it both ways anyway. Okay, that's the end of this page. I will be back in the next video. I hope you found this helpful. I will see you then.